Welcome back, everybody. Today we're going to start a new method of integration called U Substitution. All right. So we've started integrals and we integrated things like this, like x squared plus 3x plus 4 dx, right? And this was basically what I called the power rule for integration, because when we did derivatives, we had power rule for derivatives. So we basically reversed our power rule, and we wound up with the integral of x cubed over 3 plus 3 halves x squared plus 4x plus c. And this is what we've been doing the last couple of times. However, if we had something like the integral of x minus 1 the whole thing squared dx, we would then need to multiply this out to say x minus 1, right? And then x squared minus 2x plus 1 dx, something similar to this, and then we could do our power rule. But what if we had something like the integral of 3x plus 4 to the 5th power dx? Could you multiply this out? Sure. But who really wants to, right? It would be an awful lot of work to multiply this out. Now, if we were doing the derivative of 3x plus 4 raised to the 5th power, I'm going to change it to minus 4. I've done a lot of pluses. There you go. 3x minus 4 to the 5th power, we would do something called the chain rule, right, when we're doing our derivatives. However, now all right, and you remember with the chain rule, I did a substitution with a u. So I made u equal to 3x minus 4. All right, now with integrals, I also need to know what du equals, and du equals, right, 3 dx. All right. Now, basically, we need to substitute in. So all I have is a plain old dx, and here I have 3 dx. So how do I get just a plain old dx? Well, I can divide by 3 on both sides, and I get du over 3 equals dx. So now I can substitute in. I have the integral of u to the 5th times du over 3. And everything is substituted for. Now, the 1/3 is a constant. So I can always pop that out on the outside. And now I can do my power rule. So I have 1/3 u to the 6th over 6 plus c. And I'll simplify that because I know what u is. U is 3x minus 4. So I have 3x minus 4 to the 6th power over 18 plus c. And there's nothing more I can do from that. That's basically substitution in a nutshell. So the key is recognizing that you have a composite function. Anytime you have a composite function, similar to this, substitution should be the first attempt that you make. All right? And the key is deciding what u is going to be. And that's a little bit more of an art than a science. So at this point, we're going to do an awful lot of examples. Each example will have something different to bring to it. And hopefully we'll get you a little bit of experience in doing u substitution. All right? So the next example we have would be all right. So here I have something inside of parentheses raised to a power. Seems to me to be a composite function. Now the question is, what does u equal? Well, u equals, again, what has to be in the parentheses. So what has to be in the parentheses is right here. Now, it is true that my 2x over here is in parentheses, but does it have to be? No, I just wrote it that way. I could do this very easily, and the problem doesn't change at all. Whereas if I erase the other parentheses, the problem would change drastically. So x squared plus 1, and then du equals 2x dx. Hey, look! 2x dx fits perfectly. So I can rewrite with my substitution. I can go integral of u squared, and then just plain old du. Because 2x dx equals du, and I have a 2x dx right here. So then I'm going to do my integration. I get u cubed over 3. And then I'm going to substitute back. X squared plus 1 to the third power over 3. And you always got to put in the plus c. So this one worked out perfectly, right? And the key with substitution, to know that it's the right avenue to go down, is the substitution is going to work pretty well. Some people say it's got to fit like a key in a lock. It won't always quite fit like a key in a lock. For example, in this first one, right, I had plain old dx up here, and I had 3 dx down here. I had to divide by 3, but it fit pretty well. So this one fit even better. So why don't we take it up a notch? It wouldn't be me if I didn't throw in at least one trig problem right away. Now, when you have a trig with something in the parentheses, you can almost always start with U substitution right away. And what's in the parentheses is 2x plus 1. So I'm going to start with that as my u. And du is going to be 2 dx. Now, like in the first one, all I have is a dx here, and I've got 2 dx here. So in order to get my dx, I'm just going to divide by 2 on both sides, and I get 1/2 du equals dx. Now I'm going to make my substitution. I have the integral of cosine u times 1/2 du. Now the 1/2's a constant. So I can do that. And now the question is, I need to integrate cosine. So the question you need to ask yourself is, what function has a derivative of cosine? Because integration is going backwards. So I need to know what function has a derivative of cosine, and it's sine. So I have 1/2 sine u plus c, and then I need to substitute back. My u is 2x plus 1 plus c. And there you go. All right. So we're finding that U substitution kind of fits into a certain area. Let's do an example with a square root. All right, now this doesn't have a parentheses, does it? However, if I change my square root to a rational exponent, the parentheses become more apparent. All right, so what's in the parentheses is 4x minus 5. So I'm going to make that my u. And then du is 4 dx. But again, I only have a dx here, so I have to divide by 4. Now, there's a lot of different ways to do this. I like just dividing by 4 and saying 1/4 du equals dx. Your book might have a slightly different way of doing this, but you wind up in the same spot. So whichever way you want to do it is fine with me. So I have u to the 1/2, 1/4 du. And that 1/4 is a constant, so I'm going to do 1/4 the integral of u to the 1/2 du, 1/4. Now I'm going to integrate. So if when I integrate, I get u to the 3/2 and times 2/3 plus c, and then 1. So 1/4 times 2/3, I can call that 2/12 or 1/6. So I got 1/6. And then u is 4x minus 5 raised to the 2/3 plus c. All right. So now that we've done one with a square root, we've done one with a trig, we did one that was just straight algebra. Let's try one that looks like a rational function. All right. So I have the integral of e to the x dx over 3 plus e to the x. All right. So again, this is where it becomes an art versus a science. The reason I'm going to pick the bottom as my u is e to the x plus 3, because when I do I know that my next step is to do the derivative. The derivative of 3 is going to be 0, so I'm left with just plain old e to the x dx, which is what I have in my numerator. All right. If I started with e to the x as my u, I would wind up with e to the x as my du, and this 3 would just be hanging out there. All right, so this way I take care of the 3, right, over here. And then when I do my derivative, the 3 disappears, and I'm left with what's exactly in the numerator. So I have the integral of du over u, which is the integral of 1 over u times du. Either way you want to write it is fine. But what function has a derivative of 1 over u? Is the question. So when I do my integral, I wind up with ln u, because if I do the derivative of ln u, the answer is 1 over u. It's always plus c, and then I have to substitute back. There we go, and there's my final thing. So whenever I have du over u or 1 over u times du, either way you want to write it is fine, like I said. The integral of 1 over u is ln u, just as the derivative of ln x, 1 over x, just changing the letter. All right. So let's try another rational function, and let's see what we get. All right, so I have the integral of 2x over x squared times dx. Now you might say, hey, I'm just jumping right into U substitution, and you could call u equal to x squared and du equal to 2x dx, and you would probably be off on your way. All right, but what could I do first? I don't want to do this first. What I'd rather do is I'd rather simplify first. So I have the integral of 2 over x dx, which is the integral of 1 over x times 2 dx. All right. Now, the 2 is a constant, so if I put the 2 out here and I go 1 over x times dx, what did we say in the last one? The integral of 1 over x, ask yourself the question, what function has a derivative of 1 over x? And what we know that to be is ln x. So 2 ln x plus c. All right. So I'm going to give one or two more. Let's see how it goes. Sometimes you just know U substitution is the right way to go. However, things don't fit just the way you'd like them to fit. All right, so here is my problem. So we're going to do the same thing we've always done. Take the stuff that's under the radical symbol, and we're going to make it our u. So u equals 2x minus 1. And that's probably a great way to go. But du equals just 2 dx. Now you might say that's not a problem, but it is a problem. What about that x over here? Remember, if we're substituting, we got to substitute for everything. We can't do this. We can't say x u to the 1/2, right? This would be wrong. Okay? Now I'm going to erase this. And the reason it's wrong is because I can't have x's and u's in the same problem. Remember, we're in single variable calculus. Even if we were in multivariate calculus, this would still be terrible. Okay? So this is not the way to go. You can't do this. So we have to figure out something that we could take this x and turn it into something with a u in it. All right? So I'm going to take away what's wrong. Okay? So I'm still going to have the 1/2 du equals dx because that seems like it's okay. However, I'm going to take this equation and then I'm going to solve for x. So I have the integral of 1/2 times u plus 1 times u to the 1/2 power. All right. And in order to make my substitution complete, I'm going to do times 1/2 du. So basically I had three things to substitute. This, excuse me. This was the substitute for x. I'm going to change color. This was the substitute for my function. Change color one more time. This was the substitute for dx. So I had three substitutions to make. Now I've got two constants. I've got 1/2 times 1/2 is 1/4. The integral of u to the 1/2 times u plus 1. Remember, with multiplication, the order doesn't matter. However, what can I do even before I integrate? I can distribute. So I have 1/4, the integral of u to the 3/2 plus u to the 1/2, right? And I need a du out here, and I need a du over here. And now I can get to my integration. So I have 1/4, once again, u to the 5/2 divided by 5/2. Now I know that's 2/5. I'm just leaving it as 5/2 for now. All right, u to the 3/2 divided by 3/2 plus c. So I have 1/4 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. And now I'd like to just distribute the 1/4 mostly to, and then substitute back. So I've got 2/20 is 1/10. And my u is 2x minus 1 to the 5/2 plus, I've got 2/12, so that's 1/6. Not u, I'm going to substitute back. Got to substitute back for the u. A lot of people forget to do that. Don't do that, because I will take off if you don't. And there is your final answer. All right. So the last one I want to do is I just want to inject the idea of the definite integral in here. All right. U substitution can be done with indefinite integrals or definite integrals. So I have the integral from 0 to 1 of x times x squared plus 1 cubed dx. Now, the main difference between a definite and an indefinite integral is your indefinite integral has a plus c. Your definite integral is going to come down to a number. It doesn't have to be a whole number, but it's just going to be a number. All right, so let's start the way we've always done, which is what's in the parentheses is a good guess at u. Then du is going to be 2x dx. Look here, even though they're separated, I still have x dx, so I'm almost done. So that's du over 2 equals x dx. Hey, listen, my substitution fit almost perfect. 0 to 1. I'm going to take the 1/2 and just pop it out there right away, and then I get u cubed du. Now, I've almost done with my substitution. I've substituted for almost everything. There is only one thing I have not substituted for. Okay, I'll use yellow. I like yellow. All right. And that's right up here, my upper and lower limit. Now, my upper and lower limit were the same up here when my functions were all x's, right? So I call these the x limits. In order to make my substitution complete, I want to make them u limits. Now, again, there's a number of different ways to do this. I'm showing you the way I like best, all right? So if the book shows you something different that you'd like to do, and you wind up with the same answer, that's fine. However, I'm going to use this equation over here, and I'm going to say when x equals 0, u equals 1. Because I take 0, I plug it in, I get u equals 1. If I take x equals 1, 1 plus 1 is 2, I get u equals 2. So in order to make my substitution complete, I now have an integral between 1 and 2. Now, the good part about this is remember that substitute back that we were constantly doing at the end of the indefinite integral? Because I changed everything to u, and it's a definite integral, I'm not going to need to substitute back, which I think makes things way, way easier. Because now I have 1/2 u to the 4th over 4 between 1 and 2, right, as my integration. Then I have 1/8 u to the 4th between 1 and 2. Now I need to start figuring out plugging in my upper limit. So I take 2 and I plug it in. 2 to the 4th, 2 to the 3rd is 8, 2 to the 4th is 16. So I have 16 over 8, right? 1/8 times 16 is 16 over 8. Minus, right? Because I'm subtracting my lower limit. Plug in 1, I get 1/8. And 16/8 minus 1/8 is 15/8. And there is my answer. All right, like I said, there are multiple ways to do this. I'm showing you the way I like best. Thank you guys for listening. There's more practice ahead, but I'll see you next time. All right, thank you.